So the thing is that once we know the Gauss law, so Gauss law states that the net electric flux passing through any closed surface is equal to the charge enclosed by it, right? So hope for A section students and as well as B section students, the Gauss law statement and its proof and its applications all are completed, right? So for A section students, we completed potential also, right? We completed potential also in this today's class also. We completed almost potential is over, right? So for B section students, we have completed Gauss law and its applications, right? So let me go for the discussion of one important concept related to the Gauss law. From that one, we can go for the problems of Gauss law, right? So let me discuss, right? So we know that the mathematical form of Gauss law is being given as integral of d bar dot ds bar over a closed surface is equal to charge q enclosed. There is nothing but flux, electric flux xi, that is net. Meaning is that net outward flux is equal to the charge enclosed by that particular closed surface, right? So in the mathematical form, we can say that integral of d bar dot ds bar is equal to xi net, that is equal to q enclosed, right? So from this form, we go for another form of Gauss law or Gauss law by using divergence theorem, right? So hope this topic is already completed for A section students, right? So let me wait 5 minutes of time so that we can finish that one and we can go for the important problems which have been already appeared in the previous question paper several times. Let me bear 5 minutes time, right, for A section student. Right? So we know that from the Gauss law, we can say that integral of d bar dot ds bar is equal to xi net is equal to q enclosed, right? So we know that closed surface represents a value. So from the statement of the Gauss law, we can say that integral of d bar dot ds bar over a closed surface is equal to q enclosed. So this q enclosed is nothing but charge enclosed by the closed surface. So as we know that closed surface resembles or replicates a value, we can say that the charge enclosed by the closed surface is nothing but charge enclosed by the value. Charge enclosed by the value, right? So whenever charge is inside the value, and that is also of distributive nature, right? So we can calculate the charge inside a volume or charge contained in the volume by using this formula. So the formula is, we can calculate this one as Q is equal to integral of rho v dv, right? So this formula you can get it by using the charge calculation for distributive charges, right? So Q is equal to integral of rho v dv value, right? So we know that from the Gauss law mathematical statement, we can write integral of d bar dot ds bar over a closed surface is equal to charge q enclosed, right? So now in the place of q enclosed, I can substitute this formula. There is nothing but q is equal to integral of rho v dv, right? So now writing this one, you will get back integral of d bar dot ds bar over a closed surface is equal to integral of rho v dv over the value, right? So this is the thing what we are going to get after substituting this formula in the place of this one, q enclosed one, right? So we'll get back integral of d bar dot ds bar over a closed surface is equal to integral of rho v dv over value, right? So the left hand side expression, in the above equation, the left hand side expression consists of closed surface integral, whereas on the right hand side we are having a volume integral. So we know that by making use of divergence theorem, a closed surface integral can be converted into a volume integral, right? So what is the statement of the divergence theorem? All those things for A section students I already discussed in the classroom. For B section students I will discuss in the next class, right? That means in the offline mode, when we come to the classes, in the regular class, we will discuss divergence theorem and what are the statement, all those things we will discuss, right? So by using the divergence theorem, we can convert a closed surface integral into volume integral, right? Our divergence theorem basically says that the net outward flux of a vector field that is defined over a surface, over a closed surface, is same as volume integral of divergence of the vector field defined over the value. That is our statement of the divergence theorem, right? So by using the divergence theorem, this left hand term, that is integral of d bar dot ds bar over a closed surface, can be written as integral of volume del dot d bar dv. So when you write this expression, what you are going to get is integral of del dot d bar dv value is equal to integral of rho v dv value. Right? So now, in the place of this one, right? In the place of this one, I substituted this one by using this divergence theorem. Right? So now, you see on the equation 2, that is in the equation 2, the left hand side is also volume integral, and the right hand side is also volume integral. And if you see this one, both integrals are defined over a value which are representing the same structure. So, and these are connected by means of equality. So the integrands are equal. Right? Whenever two integrals are available on the both sides of equation, LHS and right hand side, right, without anything, and both are defined over the same limits, then the integrands are going to be equal. Right? So integrands, right? So you can have del dot d bar is equal to rho v. Right? So this expression del dot d bar is equal to rho v is called as Gauss law in point form or Gauss law in differential form. So we can have a Gauss law in differential form or Gauss law in point form is given as del dot d bar is equal to rho v. So this is called as this expression is called as this expression is also called as Maxwell's first equation derived from the static electric fields. Right? So hope this one I'm not discussing in the A section students. We'll come back with them. We'll come back Maxwell's first equation, Maxwell's second equations applied for electrostatics. We'll discuss later. Anyway, so del dot d bar is equal to rho v. This expression is called as Gauss law in point form. Is called as Gauss law in point form, and the integral equation. What we are having this kind of integral equation. So there is nothing but this one. The equation number 1, integral of d bar dot ds bar over a closed surface is equal to integral of rho v dv. This is called as Gauss law in integral form, and this one is called as Gauss law in point form. Right? So these two expressions are very, very important to go with the problems on Gauss law. So just we have taken the problems on Gauss law, applications of Gauss law. If any problem is asked on Gauss law, we are going to make use of this point form of Gauss law and as well as integral form of Gauss law. Both are going to be used to solve the problems of Gauss law. Right? So let me go for discussing the various problems that have been appeared in the previous question papers for Gauss law and its applications. Right? So hope wait. So next one is let's go for an important problem that has been appeared in the previous question papers. So all the problems what I am going to discuss in these classes, especially in online classes, those are very, very important problems which have been appeared in the previous question papers. Right? Please make a note in your notebook or paper so that these problems are very, very important problems. Let's see. So we'll have one important. Already the students are also represented with a big star, several number of stars on the problem. This is very, very important part. Right? So let me see this particular problem. Right? Calculate the charge enclosed, charge contained in the volume defined by the boundaries 1 lesser than x lesser than or equal to 2, 2 lesser than or equal to y lesser than or equal to 3, 3 lesser than or equal to z lesser than or equal to 4. The volume is having the flux density d bar is equal to, d bar is given as 10x square, 10xy square ax bar plus 15 x square y uy bar plus what we are having is so we can have 15 x square y uy bar plus let me wait plus what we are having is 20 x square y square. Right? So I will read out the problem. The volume is having a flux density. The flux density is being given as 10 y square. What we are we'll discuss this one. We'll discuss. So the flux density is having a 10x y square ux bar plus 15x square y uy bar plus 20x square y square uz bar. 20x square yz uz bar. So we can have what he is asking us. He is asking us to determine. Right. So I will come back to the previous slide. Right. We'll go for this one. Right. So the problem is that calculate the charge enclosed in the volume defined by the boundaries 1 lesser than or equal to x lesser than or equal to 2, 2 lesser than or equal to y lesser than or equal to 3, 3 lesser than or equal to z lesser than or equal to 4. So for this particular volume, the boundaries are given, and he is asking us to determine what is what he has given is has given the volume in the flux density. Flux density d bar is equal to 10x square 10xy square ux bar plus 15x square y uy bar plus 20x square y square z uz bar, right? So here in this problem, he is indicating the unit vectors with the u. So you can indicate the unit vectors with the a cap, right? A bar or u bar. Any format you can use. So this kind of format is using, right? So first one is he's asking us to determine the charge contained within the volume, right? So in order to calculate the charge contained within the volume, we require a volume charge density. So volume charge density we have to obtain. So once you get the volume charge density, you can get the charge contained within the volume is equal to Q is equal to integral of rho v dv value, right? So in order to get the rho v, well, rho v is nothing but what? Volume charge density. We have to make use of the Gauss law in point form. So just now we have derived the Gauss law in point form. So Gauss law in point form is del dot d bar is equal to rho v. That means divergence of flux density is equal to the volume charge density. That is the point form of Gauss law, what just now what we have derived, right? So we can have rho v is equal to del dot d bar. So del is nothing but what? Vector differential operator, what we have discussed in the first unit, right? So this vector differential operator del can be given for Cartesian system, can be given for cylindrical coordinate system, can be given for spherical coordinate system. So our task is to determine the del for, we have to make use of the del here for Cartesian system. So the del in Cartesian system is given as del is equal to dou by dou x ux bar and dou by dou y uy bar plus dou by dou z uz bar. This is the del operator in Cartesian coordinate system, right? So and we can have del dot d bar, right? So we have to substitute this d bar expression also. So d bar is equal to 10xy square ux bar plus 15x square y uy bar plus 20x square y square z uz bar, right? So now for this del operator and d bar, you have to go for the dot product between these two things, right? So we can have so when you perform the dot product between these two things, what happens? We know that dot product of a unit vector with itself becomes 1, and dot product of a unit vector with the other unit vector, which is defined in the normal direction, that is becomes 0, right? So what happens? Ux bar dot ux bar becomes 1, uy bar dot uy bar becomes 1, uz bar dot uz bar becomes 1. So remaining 6 terms will lead to 0. So we can have 3 terms will be there. So these 3 terms are retaining because of the fact that ux bar dot ux bar is equal to 1, uy bar dot uy bar is equal to 1, uz bar dot uz bar is equal to 1, right? So when you take these 3 terms only, right, and rest of the terms it becomes 0. So we can get only 3 terms, right? So those 3 terms will involve you can have this kind of things, right? So dou by dou x of 10xy square plus dou by dou y of 15x square y plus dou by dou z of 20x square y square z, right? These are the terms what you are going to get after performing the dot product, right? So now in the first term, dou by dou x of 10x y square is there, right? So that means we are doing a partial differentiation with respect to x. So this 10 and y square are being taken as a constant. So it comes out to be 10 y square, and dou x by dou x that becomes 1. And in the second term, dou by dou y of 15x square y. And we are doing the differentiation with respect to y. So 15 and x square, those are going to be treated as a constant. They comes out, right? So we'll get back 15x square, right? So, and you can see this one in the third term, we are going with the dou by dou z. Differentiation is done with respect to dou by dou z. We can have 20x square y square z is there. So only z terms are going to be retained, whereas the 20x square y square are going to be constants. They are going to be brought into outside, right? So when they brought into outside, you can have dou z by dou z. So dou z by dou z is nothing but 1. So the expression what you are going to get is rho v is equal to 10 y square plus 15x square plus 20x square y square, right? So this is the term, the what we call volume charge density. It is not a fixed one. It is changing one, right? Volume charge density, now it is changing one, right? So it is not a constant. It is changing one. So that means from one place to another place, within that volume, the charge density is varying. That's nothing but it's a non-uniform charge distribution is there inside the volume that is being given by this particular expression, right? So rho b is equal to 10 y square plus 15 x square plus 20 x square y square. It says that charge density is a function of x and y. That means if within that particular volume, the charge is changing from one location to another location. That means it is going to be a non-uniform distribution, right? So hope in the classroom we are discussing with only uniform distributions. But for non-uniform distributions, we have not seen any structure or anything. Only the thing is that we are having this kind of, in the problems, you can see this kind of approaches, right? So now what we are having is that we have got a rho b, that is the functional dependence on xy is there. So it is a scalar function, variable scalar function, right? It's not a vector, it's a scalar. It's a scalar which is having a variable dependence on x and y, right? So rho b is equal to 10 y square plus 15 x square plus 20 x square y square. If you see this kind of functions which is depending on x, y, z or any other coordinates, right? So those are going to be non-uniform distribution expressions. Make sure that one. So I think in the classroom also I given for non-uniform distributions, the problems are very, very important for competitive examination point of view, right? So that's why I'm stressing, right? So this kind of expressions, if you see in the exams or any competitive examination, that comes from the category of non-uniform distribution. Make sure that one, right? So the rho b, what you have got is nothing but there indicates that there is a non-uniform distribution inside the value, right? So once you get this particular volume charge density, now we have to get back this charge contained within that particular volume, right? So charge contained within that particular volume can be obtained by using the formula Q is equal to integral of rho v dv volume, right? Integral of rho v dv volume, right? So now by looking this flux density expression, it involves unit vectors as ux bar, uy bar, uz bar. So that means flux density is a vector which is defined in Cartesian system. So in Cartesian system, the differential volume is given as dv is equal to dx dy dz. So hope this formula you can see in the first unit, right? So dv is equal to dx dy dz, right? So now substitute this one. So integral of rho v dv value. So we'll get back. So now rho v is equal to, in the place of rho v, you can substitute 10 y square, 15 x square plus 20 x square y square. And in the place of dv, I can substitute dx dy dz. Dx dy dz, right? So now you can have three integrals. Why? Because the integral what we are doing is over the volume. You can have three integrals. So you can have a integral x is equal to 1 to 2, y is equal to 2 to 3, z is equal to 3 to 4, right? So integral of x is equal to 1 to 2, y is equal to 2 to 3, z is equal to 3 to 4. So you can have 10 y square plus 15 x square plus 20 x square y square dx dy. These are the things what you have to go. Now we have to go for solving this triple integral, right? So if you see this one now, in the rho v expression what we are having, this rho v expression is my integrand now. Now my integrand is 10 y square plus 15 x square plus 20 x square plus y square, 20 x square y square, right? So there, if you see that one, you don't have any z term, right? So z term is not there. So now what happens is, as z term is not available, so the integral from z is equal to 3 to z is equal to 4. This is the integral what we are having. That is the integral what we are having. The inner one is z is equal to 3 to z is equal to 4. So and the limit and the only variable is not having any z. Only dz term is there. Now you can solve this one, right? So integral of dz simply gives z. So and if for that z, if you substitute the limits from 3 to 4, you will get 4 minus 3. So 4 minus 3 means 1, right? So for z variable and its integral, if you solve it, you will get back only 1, right? So the remaining two integrals, you are having x is equal to 1 to 2, y is equal to 2 to 3. And the integrand is now still same as this. Why? Because we don't have any z term. So 10y square plus 15x square plus 20x square y square dx dy. dz is over. For dz we have performed the integral and we have substituted the limits. We got 1 only, right? So dx dy, right? So now how to solve this integral? For solving this integral, what we have to do? First we have to go with the inner integral. Now the inner integral is y is equal to 2 to 3. Y is equal to 2 to 3, right? When you are doing this kind of multiple integrals, first go with the inner integral, then go for towards the outer integral, right? So previously the inner integral is from z is equal to 3 to 4, that we have solved. Now the inner integral becomes y is equal to 2 to 3, right? So we have to go for this one, right? So if you observe this one, this rho v consists of 3 terms: 10y square plus 15x square plus 20x square y square. So now go for individually. So for 10y square, if you go for the integration, it becomes 10 into y cube by 3. Why? Because integration of y square dy, right? So we don't have any dx is going to be kept outside, only the dy variable is being considered, y variable is being considered. So 10 into y cube by 3 with the limits 2 to 3. And in the second term, 15x square is there. So 15x square is treated as a constant, so it comes out. So you can have y. Integration of dy is nothing but simply y. For the second term, we'll get simply y. So y's variables are limits are from 2 to 3. And in the third term, we are having 20x square y square. So take common as 20x square. You can have y cube by 3 with the limits 2 to 3, right? With the limits 2 to 3. Now substitute all those limits. Wait. Somebody. Okay. Right. I'll remove it. Yeah, okay. Please wait. So I turned on the utility board for the participants. So that's why now I made it to off. So that's why you are having that kind of lines. Okay. So what you are having is once you substitute this y limits, you are going to get 10 into 3 cube by 3 minus 2 cube by 3 plus 15 into x square. In the place of y, 3 minus 2, here 20x square into, you can have 3 cube by 3 minus 2 cube by 3. You are going to head, right? So you are going to have, and outside you are having dx, right? So now the integral varies from 1 to 2. Integral for dx case, for x variable case, you get integral 1 to 2. You can have 10 into 3 cube by 3 minus 2 cube by 3 plus 15x square, 3 minus 2 plus 20x square, 3 cube by 3 minus 2 cube by 3 into dx, right? This is the thing what you are having, right? So now if you substitute all those calculations, and if you do this one, what you are going to get is 10 by 3 into 27 by 8, 27 minus 8 plus 15x square, 3 minus 2 is 1. And here 20 by 3 x square. So here 27 minus 8, you are going to get a value of 19, right? So now if you substitute and simplify this one, you will get back integral of 1 to 2, 190 by 3 plus 15x square plus 38 by 380 by square by 380 by 3, I think 380 by 3 x square 1 into 19 is 380, right? So anyway, we'll get back 380 by 3 x square into dx, and the integrals are there from 1 to 2, right? So now we have to go for the integration with respect to x variable. So 190 by, if you go for this integration, what you are going to get? 190 by 3 x with the limits from 1 to 2. Here in the second term we are having x square, that means 15 into x cube by 3 with the limits 1 to 2, and you are having 380 by 3, right? 380 by 3 into x cube by 3 with the limits 1 to 2, right? With the limits 1 to 2. If somebody is giving the answer, they are trying to give the answer. Let me wait. Somebody has given the apply, they have given the answer. Right. So somebody is giving the answer as 591.11 C coulombs. Let me check this up. I think but the student has did a mistake that the place 393.9, I think you will get it. 393.8. Anyway, Jashwant and Kavesri has given reply this one. Anyway, we'll go for this problem, right? So the student has done a mistake that instead of 380, the student has written 38. Okay, we'll come back to this one. Right. So we'll get to 393.9 coulombs. Let me check. Please check in. We have to substitute 380. So student has written 38. It is coming around 380. Or x square by, right? With 380 only, we get 393. Now, okay, obviously has replied. Okay, anyway, very good, it's correct. So, okay, even though you write 380, you'll get back 393.9. Okay. So, when you go for the integration with respect to x, you'll get 193 by 3 x with the limits 2 to 1. And in the second term, we are having 15 x square. If you go for the integration of x square, you'll get what you are going to get x cube by 3 with the limits 1 to 2. And here 380 by 3 x cube by 3 with the limits 1 to 2, right? So you are having a 190 by 3 into 2 minus 1, 15 by 3, 2 cube minus 1 cube, and 28 by 9, 2 cube minus 1. So here 380 by 9, 2 cube minus 1, that is nothing but 8 minus 1. So after substituting all those things, you will get back 393.9 coulombs or 393.89, whatever is the case, you will get the answer of 393.9 coulombs, right? With 380 also, what the student has done a mistake here, I will write here. So you have to write here 0. Sorry, wait, I will remove it. Okay, here you have to write 380, here also you have to write 380. Then you will get the answer as 393 point. Even though you write 380, you will get 393.9 coulombs, right? So hope this is one of the important problem what we are having. So hope it is clear. Let me reply in the chat room. Reply in the chat. Hope this problem is clear. Update 402 has replied Almas Banu. Okay, we'll go for one more problem. So this problem is very important problem. Make sure that this problem is very important problem. It appears several times in the previous question papers. So let me go for one more problem. And this problem is also very important problem. All the problems what we are discussing are very important problem. Right. So I will give the description of this particular problem. Let E bar is equal to x by ux bar, x square uy bar, let E bar is equal to, right, I will repeat once again. Let E bar is equal to xy ux bar plus x square uy bar. Find first one, electric flux density D bar. Second one, volume charge density rho v. The volume charge density rho v, right? So given that, so E bar is equal to xy ux bar plus x square uy bar, right? So here ux bar, uy bar are unit vectors. So for unit vectors, you have written ux bar, uy bar, right? So you can make use of any kind of notation what we discussed in the classroom, right? So now first quantity what is asking is asking us to determine the electric flux density D bar. So we know that once the electric field strength is given, electric field strength means E bar and electric flux density means D bar, right? So once electric field strength is given, you can get back electric flux density, right? So the relationship between the electric field strength and electric flux density is D bar is equal to epsilon times of E bar. D bar is equal to epsilon times of E bar. So now we can have epsilon is equal to epsilon naught, and that is equal to epsilon naught into E bar. In the place of E bar, you can have xy ux bar plus x square uy bar, right? Epsilon naught into xy ux bar plus x square uy bar, right? So that is the D bar, right? First part is over, right? So simply D bar is nothing but simply multiplying with epsilon, right? Multiplying with epsilon will use the D bar, right? So if you do that one, you can get back, right? And he has not mentioned any medium, so we will take the medium as free space. You can write epsilon is equal to epsilon naught into epsilon r. For free space, epsilon r is equal to 1. So you'll get back simply epsilon is equal to epsilon naught, right? So now in the place of epsilon, we have substituted epsilon naught, we got this one, right? So hope it is clear to everyone, right? So second quantity is what is asking. He is asking us to determine the volume charge density rho v. So he is asking us to determine the volume charge density rho v. Let me know how to calculate this rho v. So we know that from the point form of Gauss law, what we just discussed. So del dot D bar is equal to rho v, right? So that means in order to get back the volume charge density rho v, what we have to do is we have to perform the dot product between the del operator and the d bar. So d bar just we obtained just now. In the previous step only we got del bar, we got a d bar, and del is nothing but by looking this flux density vector and electric field strength vector, we can say that the flux density and the E bar both are defined in Cartesian coordinate system. So we can say that del dot d bar is equal to rho v. So del we have to make use of del defined in Cartesian system, right? So the del is being defined in Cartesian system by making use of this formula. So that means del is equal to dou by dou x ux bar plus dou by uy bar plus dou by dou z uz bar, right? So del expression already we used in the previous problem also, right? Del can be defined in Cartesian, cylindrical, spherical, right? In any manner we can define. So now the del in Cartesian has been used by us in the previous one. In the previous problem also we used del in Cartesian. Now here also I am using the del in this problem also, right? So del in Cartesian system is being defined as del is equal to dou by dou x ux bar plus dou by uy bar plus dou by dou z uz bar, right? So now substitute both these del expression and d bar expression. So d bar expression just we now got. So rho v is equal to dou by dou x ux bar plus dou by uy bar plus dou by dou z uz bar dot product with epsilon naught xy ux bar plus x square uy bar plus x square uy bar. Now epsilon naught into, so epsilon naught is a constant that can be brought outside into dou by dou x xy plus dou by dou y x square. Right, epsilon naught into dou by dou x of xy plus dou by dou y of x square, right? So now if you observe this one now, in the first term we are having x and y. So and we are doing the differentiation with respect to x. So y comes out, simply you can have dou x by dou x. Dou x by dou x is 1. And in the second term we are having x square, right? So we are having x square here, and we are going with the differentiation with respect to dou by dou y. So dou by dou y with respect to x square is a constant. So differentiation of a constant becomes 0. So what happens is this term becomes simply 0, right? So only the first term will exist. In the first term after differentiation we'll get only y. So the thing is that what we are going to get is epsilon naught into y. So epsilon naught can be written as 8.84 into 10 to the power of minus 12 farads per meter, or that is also can be written as 1 by 36 pi into 10 to the power of minus 9 farads per meter. So by substituting this epsilon naught here, you get back up epsilon naught is equal to 1 by 36 pi into 10 to the power of minus 9 farads per meter. So that 1 by 36 pi into 10 to the power of minus 9, it comes out to be 8.84 into 10 to the power of minus 12. And simply you are having the term as y. So this is rho v epsilon naught into y. So we'll get back 8.84 into 10 to the power of minus 12 into y coulomb per meter cube, right? So this 10 to the power of minus 12 can be written as pico, right? Because pico means 10 to the power of minus 12. So we'll get back 8.84 pico, 8.84 y pico coulomb per meter cube, right? You'll get back rho v is equal to 8.84 y pico coulomb per meter cube, right? That is the answer for the charge density rho v, right? So what are the things that is asked is, first one is d bar, second one is valence charge density rho v. So both things we determined by using this simple relation. First relation is d bar is equal to epsilon times of E bar, and the second relation is point form of Gauss law, that is del dot d bar is equal to rho v, right? So with we can have this kind of problems into our case, right? And so these two problems what we have discussed in this class are very, very important problems, right? So please note these things in your notebook, right? Or otherwise take a screenshot while I'm giving the presentation or while giving the lecture. Take a screenshot and write these things in your notebook after the completion of the class. No problem what you are having, right? So, and we are having a so let me go for one more important problem. I think it makes use of So let me go for one more problem, right? So still we are having 10 minutes time is there, we can go for one more problem. Let me wait. Okay. So let me go for this problem number 4. So just we have seen problem number 1 and 2. 3 is different. 3 makes use of potential concept. So for B section students, till now we have not covered any potential concept. So that's why I'm not taking that problem. Whereas problem number 4 is also a very important problem. This is you can do that one with the things what we discussed till now, right? So just I will read out the problem, right? So given the electric flux density D bar is equal to 0.3 R square AR bar. Now he is using the notation as AR bar. Make sure that one different ways of asking the problems with the different ways of unit vector notation. Sometimes they will go U bar, A cap, anything, right? So for previous question papers, 3 varieties of unit vectors are there. Don't confuse with this kind of notations. That's why I'm clearly stressing in the classroom and as well as in online classes also. Unit vectors can be represented in 3 ways: U bar, A cap, like that one, anything you can make use of it, right? So now D bar is equal to 0.3 R square AR bar nano coulomb per meter cube, right? Flux density is having the units of nano coulomb per meter square actually. Density, no, flux density, coulomb per meter square, right? So it's not given properly. Anyway, units are done mistake by the student, it's meters. So find first one, E bar at the point P with the coordinates as R is equal to 5, theta is equal to 50 degrees, phi is equal to 90 degrees. That is the first one. And second one is total charge in the sphere having R is equal to 3. Clearly specifying R is equal to 3, right? So now by looking at this problem, we can say that he has not given any medium. He has not mentioned any medium. Medium is going to be free space. Default medium is free space, right? So from the given description, we can say that the medium is free space. So epsilon naught is equal to 1 by 36 pi into 10 to the power of minus 9 farads per meter. So this value we have to use whenever the medium is free space. Whenever the medium is other than free space, they will specify relative permittivity. So once you know the relative permittivity, so the actual permittivity can be obtained by multiplying the relative permittivity with the absolute permittivity. Absolute permittivity is nothing but permittivity of the free space, right? So that is nothing but epsilon naught, that is being given as 1 by 36 pi into 10 to the power of minus 9 farads per meter, right? So now he has given D bar now. So D bar is equal to what? 0.3 R square AR bar coulomb per nano coulomb per meter square, right? So the units are being written wrong in the problem. Nano coulomb per meter square, those are units are correct, right? So coulomb per meter square, flux density units are coulomb per meter square. So D bar is equal to 0.3 R square AR bar nano coulombs per meter square. So first one is, so he is asking us to determine first quantity, that is E bar at the given point. So point is what? P of R is equal to 5, theta is equal to 50 degrees, phi is equal to 90 degrees. At that point, he is asking us to determine the flux, electric field strength, right? So let us see how to calculate this electric field strength, right? So we know that D bar is equal to epsilon times of E bar. So E bar is equal to D bar by epsilon naught, right? So you can have D bar is equal to 0.3 R square into 10 to the power of minus 9. Why? Because he has given the flux density nano coulomb per meter square. Na? So nano means 10 to the power of minus 9. So we can have to write 0.3 R square into 10 to the power of minus 9 by epsilon naught. Epsilon naught is nothing but what? 1 by 36 pi into 10 to the power of minus 9. So that can be written as 10 to the power of minus 9 by 36 pi. So this 36 pi goes to the numerator, and 10 to the power of minus 9 and 10 to the power of minus 9 both will get cancelled. And this term, so this term and this term both will cancel, right? And this 36 pi goes to the numerator. You can get back 0.3 into 36 pi into R square AR bar, right? So that is the expression for E bar. But he is asking us to calculate E bar at a specific point. The point is given as what? P is equal to P of R is equal to 5, theta is equal to 50 degrees, and phi is equal to 90 degrees, right? Let us substitute R value here. R value is how much? As given 5. Let me now substitute this one. So now if you multiply this 0.3, if you multiply this 0.3 into 36 pi, you will get back 10.8 pi R square AR bar newtons per coulomb, right? Why? Because electric field strength will have the units of newtons per coulomb or volts per meter, right? We have seen that one. So we'll get back newtons per coulomb is given for the unit for electric field strength, or volts per meter also can give the unit for electric field strength. How the unit of volts per meter comes, we will discuss that one in the potential topic, how the unit for electric field strength comes as volts per meter, right? So you can get back E bar is equal to 10.8 pi r square AR bar newtons per coulomb, right? So now he's asking us to calculate at P, r is equal to 5, theta is equal to 50 degrees and phi is equal to 90 degrees. Now substitute r is equal to 5. In the above expression, only r term is there. We are having only r squared. So now substitute r is equal to 5, we'll get back 10.8 pi into 5 whole square AR bar Newton per coulomb. So 5 whole square is equal to 25, we'll get back 27. You'll get back 270 pi AR bar. So the 270 pi in the place of pi, if you substitute 3.14, you'll get back 848.2 AR bar newtons per coulomb. So here AR cap is there, that AR cap has been AR bar is there, that is missed by the student, right? While writing a paper, the student has missed that one, right? So you can have 270 pi AR bar Newton per coulomb, and you will get back this one as E bar is equal to 848.2 AR bar Newton per coulomb. Right? So that is the E bar expression what you are having, right? So in the second one, now we have to evaluate second one. Now what is equal to second one? We have to get back the charge contained in the space, the charge contained in the space having R is equal to, the charge contained in the sphere. The student has made a mistake there. The charge contained in the sphere having R is equal to 3. So that means we have to calculate the charge Q. So for getting the charge Q, what we have to do, simply we have to make use of first to get back rho V. So rho V can be obtained by using Gauss law in point form. So rho V is equal to del dot d bar, right? So when you get to the rho V is equal to del dot d bar, so once again del we have to substitute in a Cartesian form. So del is a vector differential operator. Del in Cartesian form we can substitute, and d bar we got it as d bar is given as 0.3 r square AR bar. So del has to be defined in a spherical coordinate system. Why? Because sorry for that one. So d bar is given as 0.3 r square AR bar, and he has given a point P r is equal to 5, theta is equal to 50 degrees, and phi is equal to 90 degrees. That means del in a cylinder spherical coordinate system we have to use, right? So del in spherical coordinate system is given as dou by dou r UR bar plus 1 by r dou by dou theta U theta bar plus 1 by r sin theta. So this 1 by r sin theta is nothing but 1 by rho also, right? So 1 by r sin theta dou by dou phi U phi bar dot product with 0.3 r square UR bar, right? AR bar or UR bar, you can write anything, right? So you can make use of this one and simply perform the dot product. If you perform the dot product, you are having UR bar term. So here also UR bar term, only UR bar terms retains, rest of the terms becomes 0, right? So you'll get back 0.3 dou by dou r r square. Dou by dou r r square. So you'll get back dou by dou r of r square means you'll get back 0.6 r into 10 to the power of minus 9. Why? Because 10 to the power of 9 is there. Why? Because it is given as nano. D bar is given as nano coulomb per meter square, right? So 10 to the power of minus 9 will be there. So you'll get back rho V is equal to 0.6 r into 10 to the power of minus 9. This is the value of rho V what we are having, right? So once you know this rho V, so rho V units are coulomb per meter cube now. Coulomb per meter cube, that is a rho V units, right? So now the question what is asked is we have to determine the charge contained within the volume. Charge Q is equal to integral of rho V dV. Integral of rho V dV. So now we can get back dV is equal to, we can have a differential value in spherical coordinate system we have to use, right? So differential value in spherical coordinate system is r square sin theta dr d theta d phi. Dr d theta d phi, right? So now if you observe this one now, he is asking us to calculate the charge within the sphere having r is equal to 3. That means he is clearly specifying the radius should be from 0 to 3. But he has not mentioned any details about the theta and phi. So that means theta and phi means we have to go for the theta and phi values what we have been used in the spherical coordinate system. So in spherical coordinate system, what? Theta varies from 0 to pi and phi varies from 0 to 2 pi, right? So now in the place of single integral over the volume, we can write three integrals, right? And if you observe this one, the differential value is r square sin theta dr d theta d phi, and you are having a 0.6 r into 10 to the power of minus 9. So this 0.6 into 10 to the power of minus 9 comes out integral of value r cube sin theta dr d theta. Then we can have a integral of r cube sin theta dr d theta d phi. Then so 0.6 into 10 to the power of minus 9. So this single integral with value can be replaced with three integrals. So first one integral r is equal to 0 to 3, and second integral is theta is equal to 0 to 5, and third integral is phi is equal to 0 to 2 pi. So we can have r cube sin theta dr d theta d phi. So you can substitute and you can evaluate these triple integral. So once again, in order to evaluate the triple integral, we have to go from the inner integral. Inner integral is first one is what? Phi is equal to 0 to 2 pi. And if you see this one, there is no phi term, only integral of d phi will be there. Then later we have to go for theta is equal to 0 to pi. Then we have to go for r is equal to 0 to 3. So first one is, but when you evaluate the inner integral phi is equal to 0 to 2 pi, what you are going to get? Simply will get 2 pi. And for theta is varying from 0 to pi, and we are having only sin theta d theta. So integration of sin theta d theta means what? You get a minus cos theta with limits from 0 to pi, right? So only sin theta and d theta are there. This is the d theta term, right? So integration of sin theta d theta, we will get back minus cos theta. So minus cos theta with limits from 0 to pi. To substitute this one, you will get back minus comes outside. In the place of theta, you can write cos pi minus cos 0. You can get back minus 1, that becomes minus of minus 2, that becomes simply 2. So this 2 and 2 pi already is there. For 5 variation, we got 2 pi. So 2 pi and 2 all will comes out 2 into 2 pi into 0.6 into 10 to the power of minus 9. This is the thing what you are going to get outside of this integral, right? So 2 into 2 pi into 0.6 into 10 to the power of minus 9, right? And you can have integral of, now only r term is there. What is that r term? R cube is there. So integration of r cube dr, where r is varying from 0 to 3. So integration of r cube will give us what? R to the power of 4 by 4. So r to the power of 4 by 4 with the limits from 0 to 3. If you substitute, what you are going to get? The same thing what you are going to get. 2 into 2 pi into 0.6 into 10 to the power of minus 9 into this 1 by 4 comes outside. So 1 by 4 into 3 to the power of 4 minus 0. So 3 to the power of 4, that's nothing but 27 into 3 is 81. 81, you get back 81. So you'll get back 81 by 4 here, and 2 into 2 pi into 0.6 into 10 to the power of minus 9 into 81 by 4. And if you substitute all those things, keep this 10 to the power of minus 9 as it is. Because nanocoulombs will get. Nanocoulombs is a normal charge value what you are going to see in your day-to-day life, right? So you will get back 152.68 into 10 to the power of minus 9 nanocoulombs, right? So this is the charge contained within the value for this particular problem what you are having, right? So 152.68 into 10 to the power of minus 9 coulombs, right? So hope